in this lecture I answer two questions. In the first question, you find out there are this semicircle inside the big quarter circle AOB, and in the second question, we find out there are this ring shape. So we start with the first question. In the drawing, we have quarter circle AOB. This is the right angle. You know that line segment OS equals to 4 units length, and you also know that RKQ equals to RQB. Again, RKQ of quarter circle AOB equals to RQB. Okay, again, our test is to find out there of this semicircle. So first of all, we define the center of this semicircle. This point is point C. And we define the touching point of the big quarter circle in this semicircle. This point is point P. CP is of course the radius of this semicircle. We define the radius of the semicircle as R, so CP equals to R. Likewise, CQ is also equals to R, it is the radius of the semicircle. Point S is the point of tendency of tangent OB with this semicircle. So we join point C and S together by a straight line. Point C is the point of the point C is the center of the semicircle. Point S is the point on the semicircle itself. Therefore, CS is the radius of the semicircle. It is equals to R according to our definition. The radius CS that is equal to R, the radius CS is drawn to point S, that is the point of tendency of tangent DB with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent DB will be perpendicular to the radius CS. If DB is perpendicular to CS, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to all one. In the next step, we will do a construction, that is to say, from point Q, we will do perpendicular on OB. Again, from point Q, we will do perpendicular on OB. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q on OB. This point is point M. Those two angles are defined as one-sided and two angles. The sum of those two angles is 90 degrees plus 90 degrees. It is 180 degrees, and because of the fact that the sum of those two one-sided triangles is equal to 180 degrees, they must be located between parallel lines. That is to say, PO is parallel to CS. So a bit quickly on 22. According to rule 22, if the sum of two one-sided triangles is equal to 180 degrees, then they are located between parallel lines. So for the following, we have line A and line B. The red line C cuts those two corners and those 2 points. Those 2 points. Those two angles alpha and beta are defined as one-sided triangles. So if the sum of those two angles alpha and beta is equal to 180 degrees, then they must be located between parallel lines. That is to say, line A is equal to line B. So if alpha plus beta equals to 180 degrees, then line A is parallel to line B. So we implemented all 22 in our drawing. We only implemented all 22 on those two one-sided triangles. The sum of those two one-sided triangles is equal to 180 degrees, and therefore it must be located between parallel lines. That is to say, CS is parallel to QM. CS is parallel to QM. Likewise, the sum of those two one-sided triangles is equal to 180 degrees, and therefore it must be located between parallel lines. That is to say, PO is parallel to QM. Here, PO is parallel to QM. So if you found out that all those 3 lines, PO, CS, and QM, are parallel to each other. Those 3 parallel lines are connected together by line 7 QP and line 7 MO. Again, those 3 parallel lines are connected together by line 7 QP and line 7 MO. And whenever you have 3 or more parallel lines that are connected together by other 2 parallel lines, then a special relationship exists between the 2 lines that connects the 3 parallel lines together. That is to say, a special relationship exists between QP and MO that connects those 3 parallel lines together. The following relationship is as follows. PC over CQ equals to OS over SM. Again, PC over CQ equals to OS over SM. So, write it down. Of course, it's according to Thell's theorem. According to Thell's theorem, PC over CQ equals to OS over SM. And again, according to Thell's theorem, in our drawing, the following version is true. That PC over CQ equals to OS over SM. PC is R, CQ is also R, OS is 3, and SM is the missing side, so limiticity. So R over R equals to 3 over SM. And again, if you remember that R over R equals to 3 over SM. R over R is 1, so 1 equals to 3 over SM. So here we multiply this equation by SM. And finding out that SM equals to 3 units in its length. This is line segment SM. This is equals to furnace in its length. In the next step, we join points Q and all together with a straight line. By joining points Q and O, we create the right triangle QOM. Point O is the center of the quarter circle, and therefore angle AOQ. This angle is the center angle because the vertex of angle AOQ is located in the center of the circle, that is point O, therefore the center angle. Center angle AOQ subtend on RKQ. Again, center angle AOQ subtend on RAQ. Likewise, this is central angle QOB that subtend on RQB. Again, central angle QOB subtend on RQB. And because of the fact that according to Moses gave us the question RKQ equals to RQB, it means that those two central angles subtend on equal arcs, and therefore they must be equal to each other in their sizes. That is to say, central angle AOQ must be equal to central angle QOB in its size. So if we define central angle AOQ as theta, then central angle QOB must be also equal to theta because they are equal to each other according to rule 23. So I click on rule 23. According to rule 23, central angles that subtend on equal arcs are equal to each other in their sizes. So in the one we have a circle. This is central angle AOB that subtend on RKB. Likewise, this is central angle COD that subtend on RCD. So if RKB is equal to RCD in its length, those two central angles, it means that those two central angles subtend on equal arcs and therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. So implemented rule 23 in our formula because those two central angles subtend on equal arcs, AQ and QB, therefore they are equal to each other in their sizes. So the size of this angle is theta, the size of this angle is also equal to theta because they are equal to each other according to rule 23. Angle AOB equals to 90 degrees. Theta plus theta is 90 degrees. Theta plus theta is 2 theta, theta equals to 90 degrees. Therefore theta equals to 45 degrees in its size. This is angle QOB that is equals to theta, and theta equals to 45 degrees in its size. The next step we'll focus on this right triangle QOB. This triangle QOB times 45 degrees equals to QM over M again. that angle QOM times 45 degrees equals to QM over MO. Repeat again, that angle QOB times 45 degrees equals to OM equals to QM over OM. Times 45 degrees is 1, so 1 equals to QM over OM. QM is the missing side and OM equals to 6. OM equals to 3 plus 3, that is 6. So 1 equals to QM, that is the missing side, over OM, that is 6. You will multiply this equation by 6. And finally, we get that the missing side QM is equal to 6 units in its length. This is the missing side QM, is equals to 6 units in its length. Write it down. In the next step, we will do a construction. That is to say, from point C, that is the center of the semicircle, we will draw perpendicular on QM. Again, from point C, we will draw perpendicular on QM. So actually, this angle equals to 90 degrees. This angle also equals to 90 degrees according to our construction. And we find the touching point of the perpendicular from point C and QM. This point is point L. When doing this construction, I can do quadrangle CLMS. Inside quadrangle CLMS, we have 1, 2 rectangles. The sum of rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing in total must equal to 360 degrees according to the rule. It states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle CLMS we have quadrangles. According to rule 5, any quadrangle that has 4 rectangles must be a test rectangle equals a square. So we relate to quadrangle CLMS as a rectangle because it has 4 right angles. But we also know that the opposite sides of an rectangle are equal to each other. So an rectangle CLSM side SM must be equal to the opposite side CL. But SM is 3, therefore the opposite side CL must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum integral CLSM, side CS must be equal to the opposite side LM. But CS is out, therefore the opposite side LM must be also equal to R units in its length. What is the length of QL? QL equals to QM minus LM. Again, QL equals to QM minus LM. So, I do that. QL, the small letter QL, equals to QM minus LM. So QL equals to QM. QM is 6 minus LM. Just like the found out that LM equals to R. So in total we should find out that QL, the short answer QL equals to 6 minus R units in its length. In the next step, I'll copy the small grain right by CQL in a new page and we'll implement the Pythagoras law on this small grain right by CQL. According to the Pythagoras law, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually this is the rectangle CQL that I copied from the original drawing. And this rectangle CQL according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, equals to QL squared plus LC squared. So QC squared is the square of the hypotenuse equals to QL squared plus CL squared. QC is R, therefore QC squared is R squared. And it equals to QL squared. QL is 6 minus R, therefore QL squared is 6 minus R squared. Plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, if you found out that R squared equals to 6 minus R squared plus 9. So R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36. Plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. So here we have r square both sides of the equation, so r square get cancelled. After I cancel r square, this side of the equation we have nothing, that is to say 0. And on the other side of the equation we have 36 plus 9 is 45 minus 12 pounds. So in total, if we found out the 0 equals to 45 minus 12 pounds. Here we will add 12 pounds to the equation. I get that 12r equals to 45. Here we divide this equation by 3. And finally we get that 12r over 3 is 4r equals to 45 over 3 is 15. So in total, if we find out that 4r equals to 15, here we divide this equation by 4, so I get that r, the radius of the semicircle r equals to 15 over 4 units in its length. The radius of this semicircle equals to r, and r equals to 15 over 4 units in its length. Our task is to find out the area of this semicircle. Actually, we know that the area of any semicircle is equals to the area of the circle, that is pi r square over 2. So the area of our semicircle must be equal to pi over 2 times r square. R is 15 over 4, therefore r square is 15 over 4 square. So the area of the semicircle equals to pi over 2 times 15 over 4 square equals to 15 squared, that is 225, over 4 squared, that is 16. So total, the area of the semicircle equals to 225 pi over 16 times 2 is 32. So the area of this semicircle the semicircle, that is the area that we are looking for this question. It is equals to either 225 pi over 32 square units inside. So in terms of numbers, the area of this semicircle equals to 22.09 square units inside. So we finished with the first question. The next step, I will present you the second question and solve the second question of this lecture. Our task in this second question is to find out the area of this green shape. So in the drawing, we have the right angle ABC. Right angle ABC is the right angle. The right angle because angle ABC equals to 90 degrees in its sides. We know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 8 units in itself, side BC, the opposite, is the missing side. Inside this right triangle ABC, we have those two identical circles. repeat again, our task is to find out the area of this green shape. So we implement the Pythagoras theorem on this right triangle BC in order to find out the length of the hypotenuse BC. Repeat again of the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABC, it means that BC squared, that is the square of the hypotenuse, equals to AB square plus AC square. And again, in the right triangle ABC, according to the Pythagoras theorem, BC square equals to AB square plus AC square. BC is the missing side, so this it is. It is BC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus AC square. AC is 8, therefore AC square is 8 squared, that is 64. So in total, we should find out that BC square equals to 36 plus 64, that is 100. So BC square equals to 100. Here we take a root out of this equation and finally get that the missing hypotenuse BC is equal to the square root of 100, that is 10. So BC equals to 10 units in its length. What is the area of this triangle, triangle ABC? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. So it's equal to the base BA times the height AC over 2. So the area of triangle ABC must be equal to the base EA times the height AC over 2. BA is 6, AC is 8, so it is 8, 6 times 8 over 2. 6 times 8 is 48, 48 over 2 is 24. So in total, we should know that the area of the right triangle ABC is equal to 24 units in its size. Okay, we can find out the area of this triangle ABC in a different way. We choose the base as BC, and the area of triangle ABC must be equal to the base BC times the height to the base that we define as h over 2. So the ABC, according to the second calculation, equals to the base BC times the height that we define as h over 2. The height h was created by the rest of the base BC. So if you found out that triangle ABC is equal to the base BC times the height edge over 2. We already found out that area of triangle ABC is 24 and it is equals to BC. BC is 10 times 8 over 2. So now if we found out that 24 equals to 10 over 2 is 5, so this expression total equals to 5h. 24 equals to 5h. Here we divide this equation by 5. And finally get the height edge to the base BC of the right triangle ABC is equal to 24 over 8 is 4.8 units in its length. So if we found out that the height edge to the base BC of triangle ABC equals to 4.8 units in its length. In the next step, we define the center of this angle. This point is point P. Likewise, we define the center of this angle. This point is point Q. We define the point of tendency of BC with this angle. This point is point L. We define the point of tendency of BC with this circle. This point is point K. Likewise, we define the point of tendency of tangent AC with this circle. This point is point J. We define the point of tendency of tangent AB with this circle. This point is point G. We define the radius of one circle as x. And because of the fact that those two circles are identical, they must be also the same on the eye. So the radius of those circles is equal to x according to our definition. So in the next step, we join points Q and K together by a straight line. Point Q is the center of the circle, point K is the point of the circle itself, therefore QK is the radius of the circle that is equal to x according to our definition. So here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius born to its point of tendency. The radius QK that is equals to x, the radius QK is 1 to point K, that is the point of tendency of tangent BC with this circle. And whenever your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius KQ. BC is perpendicular to KQ, with this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. Likewise, we join points P and L together by a straight line. PL is of course the radius of this circle is equals to x, and according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees because point L is the point of tendency of tangent BC with this circle. In the next step, we define the touching point of those two circles This point is point M, and we will do a construction, that is to say, from point M, that is the attachment point, we will do perpendicular on BC. Again, from point M, we will do perpendicular on BC. So say this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. And we find the touching point of the perpendicular from point M and BC. This point is point Z. What is the definition of line segment MZ or ZM? Actually, ZM is a common tangent that belongs to both angles. ZM is tangent to this angle, point M, likewise ZM is also tangent to this angle, the same point M. Therefore ZM is a common tangent that belongs to both circles. In the next step, we join points P and M together by a straight line. PM is of course the radius of this circle is equals to x. The radius PM is equals to x. The radius PM is drawn to point M, that is the point of tendency, and then ZM is this circle. And now radius that is drawn to the point of tendency, then tangent ZM will be perpendicular to the radius MP. If ZM is perpendicular to MP, it means that this angle equals to 90 degrees according to rule 1. Likewise, we join points Q and M together by a straight line. QM is of course the radius of this circle, equals to x. So according to rule 1, this angle equals to 90 degrees. So in the small quadrilateral PMZL, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 4 piece angle, and total was equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 piece angle is equal to 90 degrees in size. So in quadrilateral PMZL we have 4 angles. According to rule 5, any quadrilateral that has 4 angles must be its left angle plus the square. So we go to the small quadrilateral PMZL. It's a right angle because it has 4 angles. Likewise, the small quadrilateral MQKL we have 1, 2, 3 angles. And therefore this 4 piece angle must be equal to 90 degrees in its size. So in quadrilateral MQKZ we have 4 angles, and therefore it is a right angle. What about the big quadrilateral? PQ. Before that, first of all, we must prove that PMQ is one straight line. Why PMQ is one straight line? Because of the simple fact that the big angle PMQ equals to 180 degrees in size, and we know that any angle that is equals to 180 degrees in size is defined as a straight line. So PMQ is a straight line, and therefore can write to the shape PQKM is a quadrilateral. So we have one reason that PMQ is a straight line because angle PMQ equals to 180 degrees inside, therefore PMQ is one straight line. Another reason that PMQ is one straight line is according to rule 10. Those two circles and acceleration between them at point M, that is to say that touch each other accelerate at point M. Therefore, can implement rule 10. So I can calculate rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes for their touching point. In the drawing, we have those two circles that touch each other externally at point P. Point O is the center of this circle, point M is the center of this circle. The straight line that connects the circles together is of course the straight line OM. According to this rule 10, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or in other words, OPM is one straight line. OPM is one straight line. So we can definitely implement rule 10 in our drawing. Why? Because in our drawing, those two circles have an acceleration between them at point M. Point P is the center of this circle, point Q is the center of this circle. The straight line that connects the circles together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass for their touching point, that is point M. That is to say, the straight line PQ must pass for point M, that is their touching point. Or in other words, PMQ is one straight line. Again, PMQ is one straight line according to rule 10. And because of the fact that PMQ is one straight line, it means that PQ in total equals to PM plus MQ. So PQ in total equals to PM, that is X, plus MQ, that is X. So PQ in total equals to X plus X, that is 2X. PQ equals to 2X units in its length. So now we know that shape PQKL is a quadrilateral because it has four sides. 1, 2, 3, 4. This is one side. It's not divided. Point M is not dividing PQ into another part. Therefore, it is one side. Therefore, it is a quadrilateral. PQKL. In quadrilateral PQKL, we have 1, 2, 3, 4 right angles. Therefore, quadrilateral PQKL is a rectangle according to rule 5. So it is done if you found out that the big quadrilateral PQLK is a rectangle according to rule 5, because it has 4 right angles. In the next step, I'll copy rectangle PQKL in a new page, in a new drawing, and we'll draw a construction in the new drawing. Okay, we'll draw the eye to the base of the diagram ABC. here we have in rectangle PQLK, the opposite sides are equal to each other. So PQ equals to LK, the opposite side LK, but PQ is 2x, and therefore LK must be also equal to 2x units in its length. So PQ equals to LK equals to 2x. Quadrangle PQLK is a rectangle. So actually this is rectangle PQLK, the KL that I go from the original drawing. This is of course a right angle. And this is also a right angle. So in the next step we will do a construction. This is to say we will draw the height to the base BC of triangle ABC. Again, we draw the height to the base of the base BC of the right triangle ABC. The height to the base must create 90 degrees with the base BC. So from point A, we go perpendicular on BC. If we meet the height H, that is equals to 4.8 units in itself, according to what we already found out. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BC. This point is point G. Repeat again, AG is the height of the base BC, and according to our definition, AG equals to H, and H equals to 4 point units in its length. So I write it down. AG is the height of the base BC, this is equals to H according to our definition. And only found out that H equals to 4.8 units in its length. So by doing this construction, but before that we define the intersection point between the height AG and PQ. This point is point H. So by doing this construction, we created the small quadrangle PHLG. Inside the small quadrangle PHLG, we have 1, 2, 3 rectangles, and therefore the fourth rectangle is equal to 90 degrees in its size. So in quadrangle PHLG, we have 4 rectangles, and therefore it is a rectangle according to whole 5. Likewise, the bigger quadrilateral KHG, KH, we have 1, 2 factors, and therefore this 4 must be equal to 90 degrees in its size. Therefore, quadrilateral HQKG is also a rectangle because it has 4 rectangles. So we have here 3 rectangles. The small rectangles, those 2 small rectangles, and this big rectangle PQKL. Again, here, if you focus on at point on the left side of the straight line AG, AG is the height, it is definitely a straight line. So if you focus on the left side of the straight line AG at point H, here the sum of the angles must be equal to 180 degrees according to rule 3. That said that the sum of the angles in any quadrilateral is equal to 180 degrees. So which angles we have on the left side of AG at point H? We have this angle that is right angle plus this missing angle, and total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we have, if you focus on the right side of the straight line AG at point H, here the sum of the angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be also equal to 90 degrees in its size. Actually, we can prove that those 2 angles are both right angles in another way. We know that the opposite sides of a rectangle are parallel to each other. So rectangle PQKL, PQ is parallel to LK. So those 2 angles are located between the parallel lines PQ and LK, and therefore must be equal to each other in their sizes. But this angle is a right angle, and therefore this missing angle must be also equal to 90 degrees in its size according to the rule that corresponding angles between parallel lines are equal to each other. Likewise, those 2 angles are also defined as corresponding angles, and they are located between the same parallel lines PQ and LK, and therefore they must be equal to each other in their sizes. But this angle equals to 90 degrees, and therefore this missing angle must be also equal to 90 degrees in its size. So we proved in 2 different ways that those 2 angles must be both right angles. So in the next step, we join points and P together by straight line. And we join points and Q together by straight line. What is the length of line segment HG? We know that the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. So the big rectangle AQHG, side HG must be equal to the opposite side QK, but QK is X, therefore the opposite side HG must be also equal to X units in its length. We already found out that HG equals to H and H equals to 4.8. Again, HG equals to 4.8. So what is the length of the missing line segment AH? AH equals to AG minus HG. Again, AH in total equals to AG minus HG. So if you found out that the missing line segment AH in total is equal to AG minus HG. So the missing line segment AH equals to AG, that is H, and H is 4.8 minus HG. HG is X. So in total we found out that the missing line segment AG is equal to 4.8 minus X units in its length. Again, we already found out that PQ equals to 2x. PQ equals to 2x. PQ is the base of the small triangle APQ. AH is the height to the base PQ. Why AH is the height to the base PQ? Because it's greater 90 degrees with the base PQ. So in triangle APQ, the base PQ times the height to the base PQ, that is AH, must be equal to the area of this triangle APQ. So write it down. We should find out that the area of this triangle APQ in total is equal to the base PQ times the height to the base, that is AH, over 2. And again, I should find out that the area of this triangle APQ in total is equal to the base PQ times the height to the base AH over 2. PQ is 2x. PQ is 2x. We have found out that AH equals to 4.816 over 2. In total, we have found out that the area of the small triangle APQ equals to 2x times 4.816 over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. And we left only with x times 4.816. We'll open the brackets of this expression and get that x times 4.8 is 4.8x. And we have x minus x, x times minus x is minus x squared. So in total we should know that the area of the small triangle APQ is equal to 4.8 minus x squared, squared is inside. The area of the triangle APQ equals to 4.8x minus x squared, squared is inside. So in the next step, we join points P and B together by straight line. When you find the point of tendency of tangent AB with this circle, this point is point T, and we'll join points P and T together by straight line. Point P is the center of the circle, point T is the point of the circle itself, therefore PT is the radius of the circle, is equals to x. T is the point of tendency of tangent BA with this circle, and therefore according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we define the point of tendency of tangent AC with this circle. This point is point E. point E is the point of tendency of tangent AC with this circle. We join points Q and E together by a straight line. QE is of course the radius of the circle that equals to X. And according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. In the next step, we join points Q and C together by a straight line. So by doing all those constructions, we divided the big right triangle ABC into 6 parts. The 6 parts are as follows. The first part of triangle ABC is this triangle APB. The second part of triangle ABC, this is triangle AQC. The third part of triangle ABC is triangle APL. The fourth part of triangle ABC is this right triangle QKC. The fifth part of triangle ABC is the rectangle PQKL, this rectangle. And finally, the sixth part of triangle ABC is the triangle APQ. It's very clear that the area of triangle ABC in total must be equal to the sum of the areas of the 6 shapes that it consists of. The 6 shapes are the shapes that I presented to you. So, the area of triangle ABC in total it is equal to the area of the first shape, it's the area of triangle APB, plus the area of the second shape that triangle ABC consists of, is actually this triangle AQC, plus the area of the third shape that triangle ABC consists of, is actually the right triangle BPL. Plus the area of the fourth shape that triangle ABC consists of, is actually this is the right triangle QKC. Plus the area of the fifth shape the triangle ABC consists of, this is actually rectangle PQKL. Plus the area of the sixth shape that triangle ABC consists of, this is actually this is triangle APQ. So repeat again. The area of this triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. That is to say, the area of ABC must be equal to the area of the first shape, is actually the area of the triangle APB, plus the area of the second shape, that is the area of the triangle AQC, plus the area of the first shape, that is the area of the triangle PPL, plus the area of the fourth shape, that is the area of the triangle QKC, plus the area of the fifth shape, that is the area of the rectangle PQHL, plus the area of the sixth shape, that is the area of the triangle APQ. We only found out that the area of the ABC equals to 24 square meters in size, and it equals to the area of the first shape, actually the area of this triangle APB. What is the area of this triangle APB? It is equals to the base AB. it is 6 times the I to the base TP, it is x over 2. So AB times TP over 2 is 6 times x over 2. So there the first shape is equal to 6x over 2 square units in size. Plus there the second shape that triangle ABC consists of, is actually this triangle AQC. There this triangle AQC equals to the base AC times the I to the base EQ over 2. AC equals to 8, EQ equals to x over 2. So it is in total 8x over 2. Plus there are the first shape that triangle ABC consists of, there are this right triangle PBL. There the right triangle PBL equals to the base BL times the I to the base PL, it is actually x over 2. So total the area of the first shape that triangle ABC consists of is BL times x over 2. Plus there of this fourth shape that triangle ABC consists of. So what is there of this triangle QKC? The right triangle QC is equal to the base KC times the I to the base, that is KQ, that is x over 2. So there the fourth shape that triangle ABC consists of, it is equal to KC times x over 2. Now there the fifth shape that ABC consists of, is actually there of this rectangle PQKL. We know that the opening rectangle equals to the length of the rectangle times the width. The length PQ is 2x, the width PL is x. So in total it is 2x times x. Plus there are the sixth shape that triangle ABC consists of, there are the triangle APQ. We already found out that there are triangle APQ is equal to 4.8x also x squared units in its size. It's 4.8x also x squared units in its size. Okay, again, the area of the sixth shape that triangle ABC consists of is there of this triangle APQ. The total equals to 4.8x plus x squared units in its size. So, in the next step, we will simplify this long expression. Again, that 24 equals to 6x over 2 is 3x, plus 8x over 2 is 4x, plus BL times x over 2, plus KC times x over 2. So, we take x over 2 as a common factor from those two expressions, out of those two expressions. So what is left from this expression after we perform with x over 2 as a common factor? What is left is actually BL. What is left from this expression after we perform with x over 2 as a common factor? What is left is actually KC. Plus 2x times x, that is 2x squared, plus 4.8x minus x squared. So we continue to simplify this long expression and get that 24 equals to 3x plus 4x is 7x. And here x over 2 times BL plus KC. We have to turn BL plus KC, we have to express those two line segments in terms of x. So we'll be able to solve this equation only and only all the expressions will be in terms of x. So we have one equation with one expression, and one variable that is missing, that is definitely can solve. So we have to turn those two expressions BL plus KC to express them in terms of x. So here this is BL plus KC. What is the value of BL plus KC? Actually, it is very easy to see from the drawing that if you remove from BC line segment inlet, we get BL plus AC. Again, if you remove from side BC this line segment MK, we left only BL plus KC. Therefore, BL plus KC must be equal to BC, that is 10, minus LK, that is 2x. So in total, BL plus KC equals to 10 minus 2x units inside. So we found out that BL plus KC equals to 10 minus 2x units inside. Here plus 2x squared plus 4.8x minus x squared. So we have 24 equals to 7x. Here we have x over 2 times 10. 10 over 2 is 5, so this expression equals to 5x. And we have here x over 2 times minus 2 times minus 2x. Minus 2 over 2 is minus 1, so we have to only with x times minus x, that is minus x squared, plus 2x squared, plus 4.8x, minus x squared. We continue to simplify this expression and get that 24 equals to 7x plus 5x is 12x. So we have here minus x squared is minus 2x squared. Minus 2x squared plus 2x squared is 0. So those three expressions will get cancelled. And we left only 4.8x. That is 12x plus 4.8x. So in total, if you found out that 24 equals to 12x plus 4.8x. 12x plus 4.8x equals to 16.8x. In total, if you found out that 24 equals to 16.8x. Okay. Again, if you found out that 24 equals to 16.8x. Here we divide this equation by 16.8. Finally, we get that x, that is the radius of the circle, the radius of both circles, equals to 24 or 16.8 units in its length. Okay, so x equals to 24. X, that is the radius of both circles, equals to 24 or 16.8 units in its length. Our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape in total equals to the area of the big right triangle ABC minus the sum of the areas of those two circles. Repeat again, the area of the green shape in total equals to the area of this big right triangle ABC minus the sum of the areas of those two circles. So write it down. If you found out that the area of the green shape, that is the area that we are looking for in this question, in total must be equal to They have the big right triangle ABC, this is 24 square units in size. Minus the sum of the areas of those two circles. Because of the fact that those two circles are identical according to the given as equation, they must have also the same areas. Therefore, the sum of the areas of those two circles must be equal to the area of one circle times 2. The area of one circle is pi x squared. Therefore, both circles, the sum of the areas of those two circles must be equal to 2 pi x squared. One area of the two circles is 2 pi x squared. So they are the given shape in total equal to the area of the big right triangle ABC, that is 24 square units in size. Most the area of the two circles, the sum of the areas of the two circles, that is 2 pi x squared. So it is 2 pi x squared. X is 24 over 16.8, and therefore x squared must be 24 over 16.8 squared. So in total, the area of the green shape equals to 24 minus the value of this expression. Actually, the value of this expression, 2 pi times 24 over 16.8 squared, in total it is equal to 12.823 square units. 12.823 square units. Repeat again. The value of this expression in total equals to 12.823 square units in size. And 24 minus 12.83 in total it is equals to 11.177 square units in size. So if you know that the area that you are looking for in this question, it is the area of this green shape, in total it is equal to 11.177 square units in size. So we finished with the second question. In the next step, I'll summarize the lecture. We'll start with the repetition on the second question and then repeat on the solution. We start with the repetition of the first question and then repeat on the solution of the second question. In the first question, our task was to find out the area of this semicircle that is located inside this big quarter circle A or B. So in the drawing, we have, this is the big quarter circle A or B. Inside this big quarter circle we have this semicircle. We know that RKQ equals to RQB, the arcs of quarter circle A or B. In addition, we know that this is the line segment OS is equals to 4 units in its length. This is the right angle because A or B is a quarter circle. This is true for any quarter circle. This angle must be equal to 90 degrees. Again, our task is to find out the area of this semicircle. is located inside the big quarter circle AOB. So first of all, we define the center of this semicircle. This point is point C. We define the touching point between the quarter circle and the semicircle. This point is point P. And point C is the center of the semicircle. Point P is the point of the semicircle itself. Therefore, CP is the radius of the semicircle. The radius of the semicircle that we define this R. Likewise, CQ is also the radius of the semicircle that is equal to R. In the next step, point S is the point of tendency of 10 dB with the semicircle. So we join point C and S together by certain. Again, point C is the center of the semicircle, point S is the point of the semicircle itself. Therefore, CS is the radius of the semicircle that is equal to R. The radius CS that is equal to R, the radius CS is drawn to point S, that is the point of tendency of 10 dB with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then 10 dB will be perpendicular to the radius SC. If dB is perpendicular to SC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did construction. That is to say, from point Q, we do perpendicular on OB. Again, from point Q, we do perpendicular on OB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. So those two angles are defined as one-sided triangles, and the sum of those two one-sided triangles is 180 degrees, and therefore according to 22, they must be located between parallel lines. That is to say, PO is parallel to CS. PO is parallel to CS. Likewise, according to rule 22, we know that the sum of those triangles is 180 degrees, and therefore they must be located between the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, CS is parallel to QM. And CS is parallel to QM. Likewise, the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, PO is parallel to QM. PO is parallel to QM. So if we found out that all the three line segments PO, CS, and QM, they are parallel to each other. Actually, this is line segment QP that connects the three parallels together. Likewise, this is line segment MO that connects the three parallel lines together. And whenever you have three or more parallel lines that are connected between other line segments, you can implement Tell's theorem. So here, those three parallel lines are connected by line segment QP, and they are also connected by line segment MQ. According to Tell's theorem, a special relationship exists between the two line segments that connects the three parallel lines together. A special relationship exists between QP and OM that connect the three parallel lines together. The relationship is as follows. PC over CQ equals to OS over SN. Again, PC over CQ equals to OS over SN. And again, according to Tell's theorem, a special relationship exists between the two line segments that connects the three parallel lines together. The relationship is as follows. PC over CQ equals to OS over SN. PC is R, CQ is also R, OS is 3. So total PC over CQ equals to OS over SN. This is that R over R equals to 3 over SN. R over R is 1. So 1 equals to 3 over SN, and we multiply this equation by SN, and we found out that SN equals to 3 units in its length. This is the missing line segment SM that is equals to 3 units in its length. In the next step, we join points on Q and O together by side line. We join points Q and O, we created the right triangle QOM. This is the right triangle QOM. Point O is the center of the quarter circle, and for that reason AOQ is the center angle. Center angle AOQ, and this is center angle AOQ, subtend on arc AQ. Likewise, center angle QOB, subtend on arc QB. And because of the fact that according to what is given as the equation, RKQ equals to RQB in its length, it means that those two center angles subtend on equal arcs, and therefore they must be equal to each other in their sizes. That is to say, if the size of center angle AOQ equals to theta, then the size of center angle QOB must be also equal to theta because they are equal to each other, according to Rule 23. So theta plus theta equals to angle AOB, it is 90 degrees. So 2 theta equals to 90 degrees, therefore theta equals to 45 degrees in its size. This is angle theta, angle QOB equals to theta, this equals to 45 degrees in its size. So in the right angle QOM times 45 degrees equals to QM over MO. It again, the right angle QOM times 45 degrees equals to QM over OM. Times 45 degrees equals to QM over OM. QM is the missing side, OM is 6. 3 plus 3 is 6. OM is 6. Again, times 45 degrees equals to QM over OM. QM is the missing side, and OM is 6. Times 45 degrees is 1, so 1 equals to QM over 6. Here we multiply this equation by 6, and find out that QM equals to 6 units in itself. This is the missing side QM, that equals to 6 units in itself. 6. In the next step, we did another construction. That is to say, from point C, that is the center of this semicircle, we draw perpendicular on OM. Again, from point C, we draw perpendicular on QM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and QM. This point is point L. By doing this construction, we created quadrilateral CLMS. In quadrilateral CLMS, we have 1, 2, 3 triangles, therefore the fourth missing must be equal to 90 degrees in its size. Therefore, quadrilateral CLMS is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle CLMS, side CL must be equal to the opposite side SM, but SM is 3, therefore CL must be also equal to 4 units in its length. Likewise, according to the sum rule, in the sum rectangle CLMS, side CS must be equal to the opposite side LM, but CS is out, therefore the opposite side LM must be also equal to 1 unit in its length. What is the length of the missing line segment QL? QL equals to QM minus LM. Again, QL equals to QM minus LM. So QL in total equals to QM, that is 6, minus LM, that is also. In total, QL equals to 6 minus 1 in its length. In the next step, we call it the right triangle QCL, the right triangle QCL. In the Olympiad, we implemented the Pythagoras theorem in this right triangle QCL. This is the right triangle QCL that according to the result of it. According to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, must be equal to QL squared plus LC squared. QC is out, therefore QC squared is R squared, and it equals to QL squared. QL is 6 minus 1, therefore QL squared is 6 minus 1 squared, plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, R squared equals to 6 minus R squared plus 9. So R squared equals to 6 minus R squared. Here we open the brackets of this expression, and find out that 6 minus R squared equals to 6 squared, that is 36. 36 plus R squared, minus 2 times 6 times R, that is minus 12R plus 9. We have R squared on both sides of this equation, so R squared is cancelled. After cancelled R squared in this side of the equation, we left with nothing, that is to say 0, while on the other side of this equation, we left with 36 plus 9, that is 45, minus 12R. So total we should find out that 0 equals to 45 minus 12R. We added 12R to this equation, and we found out that 12R equals to 45. Here we divided this equation by 3, and we found out that 12R over 3 is 4R, and 45 over 3 is 15. So in total 4 equals to 15. Here we divided the equation by 4. We found out r, that r, the radius of the semicircle, equals to 15 over 4 units in its length. Our task is to find out the area of this semicircle. Actually, we know that the area of any semicircle equals to the area of the circle, that is pi r squared over 2. So it is pi over 2 times r squared. R is 15 over 4, therefore r squared is equal to 15 over 4 squared. So it is pi over 2 times 15 over 4 squared. 15 over 4 squared equals to 15 squared, that is 225 over 4 squared, that is 16. So in total, the area of the semicircle equals to 225 pi over 16 times 2, that is 32. The area of this semicircle equals to either 225 pi over 32 square units in size, or in terms of numbers, the area of this semicircle equals to 22.09 square units in size. So finished with the repetition of the first question. In the next step, I repeat on the solution of the second question. In the second question, our task was to find out the area of this green shape. So in the drawing, the triangle ABC. This is the right angle. Side AB of triangle ABC equals to 6 units in its length. Side AC of triangle ABC equals to 8 units in its length. So inside the triangle ABC, we have those two identical circles. Again, our task is to find out the area of this green shape. So, in the first step, we found out the missing hypotenuse, BC, of triangle BC. According to the Pythagoras theorem, in the triangle BC, BC squared, that is the square of the hypotenuse, was equal to AB squared plus AC squared. And again, the triangle ABC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, was equal to AB squared plus AC squared. BC is the missing side, so we leave it as it is. AB is 6, therefore AB squared is 6 squared, that is 6 squared, that is 36, plus AC squared. AC is 8, therefore AC squared is 8 squared, that is 64. So in total, BC squared equals to 36 plus 64, that is 100. BC squared equals to 100. Here we took a root out of this equation and found out that the missing hypotenuse BC equals to the square root of 100, that is 10. BC equals to 10 units in its length. The next step, we found out the area of this triangle ABC. The area of triangle ABC must be equal to the base AB times the height of the base AC over 2. And again, the area of triangle ABC equals to the base BA times the height AC over 2. BA is 6, AC is 8, over 2. 6 times 8 is 48. 48 over 2 is 24. So in total, we should find out that the area of the right triangle ABC equals to 24 square units in size. In the next step, we found out the area of this triangle ABC in a different way. We choose the base as BC. So the right triangle ABC must be equal to the base BC times the height to the base BC that we define as edge over 2. The height to the base BC must get 90 degrees with the base BC. So edge must get 90 degrees with the base BC. So found out the triangle ABC in a different way. The triangle ABC equals to the base BC times the height of the base BC, that is edge over 2. BC is 10, edge is the missing side, so it is in total this expression equals to 10 edge over 2. 10 over 2 is 5, so in total this expression equals to 5 edge. So 24, we know that the triangle ABC is 24. We found out that the triangle ABC is 24, so the triangle ABC is 24, that equals to 5 edge. Here we divided the equation by 5 and found out the that the height of the base of triangle ABC, and the height of the base edge, the height of the base BC of triangle ABC equals to 24/5, that is 4.8 units in its length. So the height to the base BC, let's write 90 degrees of the base, the height H equals to 4.8 units in its length. In the next step, we define the center of this circle. This point is point P. We define the center of this circle. This point is point Q. Because of the fact that those two circles are identical, they must have also the same radii. We define the radius of this circle as x, therefore the radius of this circle must be equal to x. We define the point of tendency of BC with this circle, this point is point N. We define the point of tendency of BC with this circle, this point is point K. Likewise, we define the point of tendency of tangent AB with this circle, this point is point G. Likewise, we define the point of tendency of tangent AC with this circle, this point is point J. In the next step, we join points P and L together by a straight line. Point A is the point of tendency of tangent BC with this circle. We join points P and L together by a straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that is equal to x. The radius PL is equal to x, the radius PL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all one. Likewise, we join points Q and K together by a straight line. QK is the radius of the circle that is equal to x, and according to all one, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, in the next step, we define the touching point between those two circles. This point is point M. And then we did the construction. That is to say, from point M, we draw perpendicular on BC. Then from point M, that is the touching point, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point M and BC. This point is point Z. So, by doing this construction, we created the small quadrilateral PMZL. Inside the small quadrilateral PMZL, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, the must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral PMZL we have 4 rectangles, and therefore it is a rectangle, according to rule 5. Likewise, this is the small quadrilateral MQKC. Inside the small quadrilateral MQKC we have 1, 2, 3 rectangles. Therefore this fourth missing angle must be equal to 90 degrees in its size, and therefore quadrilateral MQKZ is a rectangle. It is a rectangle because it has 4 rectangles. So those two quadrilaterals, they are both rectangles. So what PMQ is one straight line. Why PMQ is one straight line? Because of the fact that angle PMQ equals to 90 degrees plus 90 degrees is 180 degrees. And we know that any angle that equals to 180 degrees in its size, it is defined as a straight line. So PMQ is a straight line. Actually, I proved in a different way that angle PMQ must be a straight line. According to rule 10, angle PMQ must be a straight line. Those two circles have an external between them at point M. That is to say, they touch each other externally at point M. So, you can take on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. So in the moment we have those two circles that touch each other at some line, it's point P. Point O is the center of this circle, point M is the center of this circle. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching points. That is point P. Again, the straight line OM must pass through point P. That is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because those two circles have an extra between them at point M. And therefore we can implement rule 10. The center of this circle is at point P. The center of this circle is at point Q. The straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point M, that is their touching point. Again, the straight line PQ must pass through their touching point, that is point M. Or PMQ is one straight line. Again, PMQ is one straight line, so we put in two different ways that PMQ must be a straight line. And because of the fact that PMQ must be a straight line, it means that PM plus MQ equals to PQ. Again, PM plus MQ equals to PQ. Here PM is of course the radius of the circle, that is M. Likewise, QM is also the radius of the circle, that is M. So PMQ in total equals to PM, that is X, plus MQ, that is also X. X plus X is 2X. So in total we should find out that PQ equals to 2X units in its length. So we have quadrilateral PQ and PQKL. Why it is quadrilateral? Because PQ is a straight line. So in quadrilateral PQKL we have 1, 2, 3, 4 right angles, and therefore it is a rectangle. So the big quadrilateral PQLK is a rectangle because it has 4 right angles. We know that the opposite sides of rectangle are equal to each other. So rectangle PQKL, side PQ must be equal to the opposite side LK. But PQ is 2x, and therefore LK must be also equal to 2x units in its length. LK is 2x. In the next step, I copied rectangle PQKL in your page, and we drew the I to the base BC. That is H. We drew the I to the base BC. That is H in the new drawing. Actually, this is rectangle PQKL that I copied from the original drawing. And repeat again, PQKL, PQ equals to 2x, LK equals to 2x, and so I mentioned before, PQKL is a rectangle. So we have 3 rectangles. Those 2 small rectangles and the big. Okay, so we have rectangle PQKL. Again, PQ is 2x, LK is also 2x. So in the next step, as I mentioned before, we did a construction. Actually, we created the I to the base BC. The I to the base BC is defined as H. So from point A, we go perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BC. This point is point G. So, as I mentioned before, AG is the I to the base, that is H. AG equals to R, and to H it is the I to the base, that is equals to 4.8 units, according to what is given us in the question. Okay, then AG equals to 4.8 units in its length. We define the intersection point between AG and PQ. This point is point H. By doing this construction, we created those 2 small quadrilaterals. In quadrilateral PHGL, we have 1, 2, 3 right angles, and therefore this 4 pieces must be equal to 90 degrees in size, and therefore it is a rectangle. Likewise, in the other quadrilateral HQKG, we have 1, 2, 3 rectangles, and therefore this 4 pieces must be equal to 90 degrees in size, and therefore quadrilateral HQKG is a rectangle because it has 4 rectangles. So all those 3 rectangles, those quadrilaterals are rectangle, and the big quadrilateral PQKL is also a rectangle. So we have here 3 rectangles in the drawing. So those two angles are both right angles. If we focus on the right side of the straight line AG, at point H, if the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of AG at point H? We have this is the right angle plus this missing angle, so that must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, in the left side of the straight line AG at point H, the sum of the angles must be equal to 180 degrees according to all three. Which angles we have on the left side of AG at point H? We have this is the right angle plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. I proved in another way that those two angles must be equal, both of them must be equal to 90 degrees. We know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle PQKL, side PQ must be parallel to the opposite side LK. Those two angles are defined as corresponding angles and are located between the parallels PQ and LK, and therefore must be equal to each other in their sizes. But this is a right angle, therefore the missing angle must be also equal to 90 degrees in size according to the rule that corresponding angles between parallels are equal to each other. Likewise, those two corresponding angles are located between the same parallels PQ and LK. Therefore, they must be equal to each other in their sizes. But this is a right angle, therefore this missing angle must be equal to 90 degrees in its size. So, in the next step, we join points N P together by side line and join points N Q together by side line. As I already mentioned before, PQ equals to 2x, here PQ equals to 2x. So, in triangle APQ, the base PQ equals to 2x, and the height to the base AH equals, we have the height to the base AH. So what is the length of the height to the base AH? First of all, we know that AH equals to AG minus HG. Again, AH, the missing 97 AH equals to AG minus HG. Here we know that the opposite sides of a rectangle are equal to each other, so in this rectangle, QH equals to HG. So QK equals to HG. So QK is X, therefore HG must be also equal to X units in its length. So in total, AH equals to AG, that is H, this is the height to the base, BC, that is H, and H is 4.8 also, of course, minus HG, that is X. So in total, AH equals to 4.8 minus X. And AH equals to AG, that is 4.8 minus HG, that is X. So in total, AH equals to 4.8 minus X units in its length. Therefore, this triangle APQ must be equal to the base PQ times the height to the base AH over 2. PQ is 2x, AH is 4.8 minus x. Okay, the small triangle APQ must be equal to the base PQ times the height to the base AH over 2. PQ is 2x, AH is the height is equals to 4.8 minus x over 2. We have 2 in the numerator, 2 in the numerator, so 2 will get cancelled, and we have 2 with x times 4.8 minus x. We open the brackets of this expression, x times 4.8 is 4.8x, and we have x times minus x is minus x squared. So in total, if you found out that the area of this triangle, the small triangle APQ, in total it equals to 4.8x minus x squared, squared in size. In the next step, we join points P and Q together by side line. And define the touching point of the tangent. We have tangent AB, that is tangent. Actually, join points P and Q together by side line. And actually define the point of tendency of tangent AB. This point is point T. And then we join points P and T together by side line. PT is the radius of the second is equals to x, and because of the fact that point is the point of tendency of tangent AB, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we join points Q and C together by a straight line. We define the point of tendency of tangent AC with this circle. This point is point E. And we join points Q and E together by a straight line. Q is the radius of the circle that is equals to x, and according to 1, this circle equals to 90 degrees, this circle also equals to 90 degrees. So, by doing all those constructions, we divided the big right triangle ABC into 6 parts. The first part of triangle ABC is this is triangle APB. The second part of triangle ABC is this triangle AQC. The third part of triangle ABC is the right triangle BPL. The fourth part of triangle ABC, this is the right triangle QKC. The fifth part of triangle ABC this is the rectangle PQKL, and the sixth part of triangle ABC is triangle APQ. It's very clear that the area of triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. So, the area of triangle ABC in total must be equal to the area of the first shape, that is the area of triangle ABP, plus the area of the second shape, that is triangle AQC, plus the area of the third shape, that is the right triangle PBL, plus the area of the fourth shape, that is the right triangle QKC, QKC, plus the area of the fifth shape that triangle ABC consists of, that is the rectangle PQHL, plus the area of the sixth shape that triangle ABC consists of. What is the area of the third shape? Triangle ABP. The area of triangle ABP in total equals to the base AB times the height of the base TP over 2. AB is 6, TP is x. Therefore, in total, the area of the triangle ABP must be equal to 6x over 2. So the area of the first shape must be equal to 6x over 2. Plus the area of the second shape. The second shape is this triangle AQC. What is the area of this triangle AQC? It is equals to the base AC, that is 8, times the height EQ, that is x over 2. So total, the triangle ABC and the triangle AQC, the second shape must be equal to 8x over 2. So the area of the second shape in total equals to 8x over 2, plus the area of the first shape, this is the third shape of triangle ABC, that is triangle PBL. The area of this triangle PBL equals to the base BL times the height LP over 2. LP is x, so in total, the area of this triangle PBL must be equal to BLX over 2. Now the third shape is equal to BLX over 2, plus the area of the fourth shape. What is the area of this fourth shape? It is equal to the base. This is the triangle QKC. The area of this fourth shape equals to the base KC times the height of the base KQ over 2. KQ is x, so in total the area of this triangle QKC must be equal to KC times x over 2. So the area of the fourth shape in total it is equals to KC times x over 2, plus the area of the fifth shape that is consists is actually rectangle PQKL. The area of a rectangle equals to the length of the rectangle times the width over 2. The length PQ is 2x, the width PL is x. So in total it is 2x times x. So the area of the fifth shape that everything consists of is 2x times x. Plus the area of the sixth shape, that is the area of this triangle APQ. We only found out that the area of this triangle APQ in total it is equals to 4.8x minus x squared, squared in size. In the next step, we simplify. So, the area of triangle ABC is 24 squared in size. So, in the next step, we will simplify this long expression. So, 24 equals to 6x over 2 is 3x, plus 8x over 2 is 4x, and we have here BL times x over 2 plus KC times x over 2. Here we took x over 2 from as a common factor from out of those two expressions. So we took x over 2 as a common factor. What is left from this expression after we took from it x over 2 as a common factor? What is left is actually BL. Likewise, what is left from this expression after we took from it x over 2 is a common factor? What is left is actually HC. So actually KC. So in total, the sum of those two expressions is equals to x over 2 times BL plus HC. Okay. 2x times x is 2x squared plus 4.8x minus x squared. Continue to simplify this normal expression, and we got that 24 equals to 3x plus 4x is 7x. Here we have x over 2 plus BL times HC. What is the value of BL plus HC? If we this is actually KC. What is the value of BL plus KC? What is the sum of the length of those two line segments, BL plus KC? On the drawing, it is very easy to see that if you remove from side BC this line segment MK, we get what is left, BL plus KC. Okay, again, if you remove from BC this line segment MK, we left only BL plus KC, and therefore BL plus KC must be equal to BC minus LK. BC is 10, LK is 2x. So in total, BL plus KC equals to 10 minus 2x units in its length. And again, BL plus KC in total equals to 10 minus 2x units in its length. And we have 2x squared plus 4.8x minus x squared. Continue to simplify this from equation. So we have here 24 equals to 7x. Open the brackets here. X over 2 times 10 is 10 over 2 is 5, so in total it is 5x. And we have x over 2 times minus 2x. We have minus 2 over 2 is minus 1, so in total it is x minus x times minus x. This is minus x squared plus 2x squared plus 4.8x minus x squared. So 24 equals to 7x plus 5x is 12x. And here minus x squared is minus 2x squared, and minus 2x squared plus 2x squared is 0. So those three expressions will get cancelled, and we left only with 4.8x. So total 24 equals to 12x plus 4.8x. 12x plus 4.8x equals to 16.8x. So total 24 equals to 16.8x. And again, I should find out that in total 24 equals to 16.8x. Here we divided this equation by 16.8, and finally found out that x, that is the radius of the both circles, is equals to 24 over 16.x units in its length. Our task is to find out the area of this green shape. What is the area of this green shape? It is equals to the area of the big triangle ABC minus the sum of the areas of those two circles. And because of the fact that those two circles are identical, they must have also the same areas. And therefore the sum of the areas of those two circles must be equal to the area of one circle times 2. The area of one circle is pi x squared, so it is 2 pi x squared. The sum of the areas of those two circles equals to 2 pi x squared. So the area of the green shape in total equals to the area of the big rectangle ABC minus the sum of the areas of those of the two circles, in total 2 pi x squared. The area of the rectangle ABC is 24, and we have 2 pi x squared. So it is 2 pi x squared. X is 24 over 16.8, and therefore x squared is 24 over 16.8 squared. So it is 24 minus the value of this expression. The value of this expression in total equals to 12.823. 24 minus 12.823 equals to 11.177 square is inside. So in total, we should find out that the area that we are looking for this question, that is the area of this green shape, is equal to 11.177 square units in its size. Okay, thank you very much.